Well, we got a good lab today, but let's go through the lab so that you can see what I'm talking about. So when I look at the lab handout, the whole goal is to predict and measure the index of refraction of the acrylic. We're going to use that using Snell's law. And then we're going to predict the critical angle using two different methods. And then there's a short piece on polarizing angles. And it's not with microwaves. I don't know why I have microwaves. We're using visible light because we don't have microwave sources here. And ultimately, what you're going to see here is that it's a fairly straightforward application of Snell's law. You're going to have to assemble a laser without, and you're going to see that you're going to need a resistor to add to this thing because the laser is pretty bright. And we'll look at that. And so it's going to be really important that you create a distribution curve. You've seen that I'm taking off, if you don't do a distribution curve, because that's really the core of science, I immediately take 2 points off no matter what. And then I start taking off points for not showing calculations. So there's some of you that are getting 5 or 6 points because you're not doing distribution curves and you're not doing calculations. There's only one lab that I could think that you didn't do a calculation. And then part 2 here, we're going to measure the critical angle, which I enabled theta C1 and theta C2. And I think setting this thing up is a little bit tricky. And so I think I'll try to help you with that. And on this third part, I might just leave you all to your own. Okay, just leave you all by yourself to do that. Because I think I'm going to make the lecture too long if I actually do that. But I think it's fairly straightforward. We want to go in, part 1. We want to look at Snell's law. Okay, so our first part is Snell's law. And what we're going to do here is that I think you should really pay attention to how I set this up, okay? Because the way I set this up really will make it to your advantage for it being easy. So when I look at this thing, here's what I have. I have my piece of paper, okay? Here's my piece of paper. And then what I'm going to do here is that then I'm going to have my clay. Okay, there's my paper and clay. So here's my paper. And then what I'm going to do is I'm going to squish my laser onto this setup here, just like I showed you here. So now I'm going to have my laser here, and it's a gold laser. So let's say that's the gold. And you're going to see that there's a red wire and a blue wire. Now what you're going to do here is that you're going to take a half circle. So when you look at my half circle here, you're going to pull this guy out of your kit, and you also have a protractor. So these are the two things that you're going to need in this lab here. Okay, now let me go share my screen again. You want to really orient the half circle. So in other words, you're going to take your half circle. Let's give it a nice color here. How about if we do this? And you're going to orient it this way, right? Here's your half circle. And then what you're going to do here is that you're going to shoot the laser at this guy. So as I shoot the laser is going to come out. And then you're going to see that there's going to be some refraction. And then the light's going to leave again. Now, it doesn't look parallel like this, but this is what we're doing here. And what you're going to see here is that in this case, our boundary is the air, And then the other boundary here is for the acrylic. And you can see that this is the boundary right here. So ultimately, what we're going to do here is that we're going to apply Snell's law to this. So we're going to apply Snell's law from air into acrylic. So that means we're really taking the index of refraction of air. We're going to measure some angle theta 1. And then we have the acrylic index of refraction. And we're going to measure the refraction angle. And from this, we're going to compute N of the acrylic. And you're going to see that it's going to be really the ratio of these two angles that we measure here. Okay, so we're going to measure the index of refraction relative to these angles. So what do I want you to do? I want each individual person to make 3 measurements. And then set up a table. So that means I'm going to have theta 1 in units of degrees. I'm going to have theta 2 in units of degrees. And then what I want you to do here is that I want you to get your index of refraction for acrylic. Okay, so that means I want you to do this 1, 2, 3 times. And then once you get your index of refraction 3 different times, then I want you to get an average index of refraction. And this is what I'm going to want you to load into the Canvas, not the Canvas, but the Google Sheet class, which I've already set it up. Okay, so let's look at these details here. So the way I'm going to look at these details here is it turns out that I have my applet already set up here. And what you're going to do here is that you're going to get this type of scenario here. So let me go share my screen with you. So here's the same situation here. So what you can do here is that what I would do is that I would make a measurement right here. Okay, so if I look at this scenario here, what you're seeing here is that I have my laser system, of course. And the first thing that I would do here is that I would do the following thing. I would come into my sheet. I would take my laser, put it onto a sheet. And what you're going to do here is that you're going to effectively draw, what am I going to draw here? You're going to set it up in such a way that you can rotate the half circle while keeping the laser fixed on a sheet of paper. And then what you're going to do here is that you're going to mark 3 points and draw the boundary of the half circle onto the half sheet. So let me go share my screen with you, but essentially what you're going to do here, just to make sure that we're clear, once you make this measurement, and I'll show you how to do that, then what you can do here is that you can rotate to get a different angle. Now I have a different angle. Right now I can move it up, and then I'm going to say, then rotate it again, get a different angle. So you can make 3 measurements of the incident and the refracted angle quite quickly. But you're going to see that one of the things that's going to be important is that you're going to have to figure out the normal, and you're going to need a protractor. Okay, so how do I get this normal here? The first thing that you want to do here is that you want to rotate this thing to 90 degrees. So let's say that this is, so I'm going to take that that hash mark, okay, I'm going to take this hash mark and I'm going to take this guy right to this boundary right here with those two, and then I'm going to rotate this guy till this thing is parallel to the surface. So now let's say that that's parallel to the surface. So 90 degrees would be, if this is the angle 0, then 90 degrees, if I make that my angle 0, 90 degrees then is at this point. So I would literally come in here and I would put a point here at 0. So let me get an image of this thing just so that I could show you in a moment what I'm talking about. So let me go share my screen now and just show you what I mean. Okay, so here is my screen. So you could see what I'm setting up here is that I have the laser, which remember, you're going to have that already. And what we're going to do here is that now that you have the laser and you do that, remember, keep this thing fixed, right? This is fixed. The half circle is rotated to get 3 angles. Okay, so that's the thing that you want to do. Now, what I'm going to say here is that now that we have that, let's do the setup here. So the setup goes like this. So the first thing that you want to do here is that you want to draw the boundary line of half circle. So what do I mean by that? Literally, I come in with my little protractor. And I'm going to come in and I'm going to draw a boundary line. So here I go. This is my boundary. Okay, there's my boundary line. Right? This is my boundary line. And then the next thing that I'm going to do here is that I'm going to draw 3 dots. So now draw 3 dots, incident and refracted rays. So here I go. So I'm going to take 1 dot and look what I'm going to do. I'm going to put it right here. Then I'm right where there's the interaction at the boundary, I put another dot, and then I put another dot where the ray is at, like this. Okay? So now here's what I'm going to do here. So now what I'm going to do here is that I'm going to, oops, I did not mean to move that. Let me do that again. Let me try this one more time. Something funky happened here. So what I'm going to do here is that I'm going to move this for a moment. And then I want to copy this. I'm going to place it down here. So now what I'm going to do here is that I'm going to come and put this back because this is really where we want that thing to be at. Okay. So now what you're going to do here is that the second thing that I want to, you know what? I'm going to move this over here. I need the space. So now 2, you want to remove half circle. And what you're going to find here is that, check this out. You're going to have 3 dots, right? Let me see if I can move this over here so that I have more space here. So this is what's going to be left on your paper here. So now take your line here and now take your protractor, and what I'm going to do here is that I want to extend the rays now. So this is my laser line. Okay, so this is my incident ray. Okay. And now I want my refracted ray. And you want to draw these lines big, nice and long. So then I'm going to connect the next two dots so that it looks like this. And look how long I'm drawing them. This is the refracted ray. So now I need the normal. Now remember, what you do here is you take your protractor and you put it on the dot that you're looking at, where at the boundary here, and you gotta identify the 90-degree point. So this point right here is my 90-degree point right there, just like I showed you before. And so now what I'm going to do here is that I'm going to create a normal. So now I got to draw a line from this 90-degree point all the way across. So now this is my normal. So then check this out. Now I have my angles. This is my angle theta 1. This is my refracted angle theta 2. So what do I want you to do? Okay, remove the half circle and draw in the incident and refracted rays. And what is it? The normal and angles theta 1 and theta 2. Now that what you can do here is that measure theta 1 and theta 2 using the protractor. Okay, so guess what? And then what do I want you to do? Put them into the table. Right? Put them into the table. And repeat this process, what? 3 times. Right? Repeat this process for 3 different incident angles. So eventually what you're going to do here is that once you have this, then what you're going to find here is that you're going to get to 4 here. And then what you want to do here is that from your, so then what you want to do is that you want to enter your average into the Google Sheet for this class and get n of class plus or minus 2 standard deviation of the mean like this. So that means you have what? You have your confidence interval. Now plot this thing. Plot confidence interval. So now that you have a measurement, here's what you're going to find here. You're going to have a curve. You're going to have a distribution curve. You're going to have what? You're going to have n minus 2 sigma. You're going to have n plus 2 sigma. So that means this is your confidence interval right here. Right? Here's your confidence interval. The question is this. If n of acrylic lands here, then, right, if this is end of acrylic over here, then we know that this is inconsistent with measurements. If it lands here, then we say it's consistent. Tell me whether it's consistent or not. 5. Answer the questions. Now what you're going to find here is that N of acrylic is equal to 1.49. See if this N of acrylic value falls within the class confidence interval. That's what you do with part 1. Okay? So there's part 1. Let's go to part 2. Part 2 here is that what we're going to do here is that we're going to be, what we're going to do here is that we're going to predict and measure the critical angle. Right? We're going to go do that. And what you're going to see here is that there's 2 methods. Okay? We're going to use 2 methods. So this is method 1. Method 1 here is that we're going to, this one's, we're going to use the half circle. It is important that your half circle has the piece of paper on the bottom. Okay? And so what you're going to do here is that you're going to put the clear top up and you're going to put the paper side down. Okay? And you're going to see that we need that for both methods here. So let's go look at that setup here. So what I'm going to do here is that I'm going to go share my screen. And so what I'm going to do here is I'm going to get rid of the protractor. Now, what we're really looking at is that we're looking for total internal reflection. So what I'm going to do here is that now I'm going to rotate this guy around like this. I'm going to get rid of the normals here. And what you want to do here is that you want to get it so that the rays here, make sure, why am I not, what's going on? I need to, oh, I think I got to rotate this guy. There we go. That's important here. So note that I've rotated this thing here. Let me get the angle a little bit better. Okay, this is really important. So what you're doing here is that this time the flat part of the circle is the other way. Okay, we want that flat part. Now, here's what critical angle is. So what we're really focusing on here, let me move this down just, no, I think I'm going to keep it. I want to move this guy down a little bit more. I want that ray to come. I think I'm going to have to rotate this guy like this. Okay, here's what we want. So what I'm going to do here is that I want to get a copy of this and I want to take this in here. So what's super important here is that the way we know that we're going to get total internal reflection here is when the ray goes parallel to the surface here. What do I mean by that? Well, what I'm going to do here is that, look what I'm going to do. I'm going to keep adjusting this guy. And note that as I do this, note that the angle is actually increasing. So I'm starting, you know what? I got to do this differently. I got to go share my screen just to make sure that we're clear. Nope, I did not go where I wanted to go. Sorry. So here's what we're doing here. What we're doing is that we're not, so in order to get total internal reflection, light must go from higher to lower index. So we're not looking, this ray out here, we don't care about. We only care about the ray that's inside. So in other words, I'm looking at this ray right here. So this ray here is the incident ray. And this ray right here is the refracted ray. And so that means here, if this is N1 and this is N2, I can get total internal reflection because I know in this case here that N1 is greater than N2. So the idea here is that the critical angle only occurs when the refracted ray is parallel to the to that line right there. So the critical angle only occurs when the refracted angle, and remember, this is going to be the refracted angle right in here. When this angle, theta 2, when the refracted angle, theta 2, is 90 degrees. It's got to be parallel to the surface. Let's go get that picture here. So what I'm going to do here is that I'm going to go back and share my screen. So what I'm going to do here is that I'm going to keep adjusting this guy and look at the ray now. At some point, that ray has to, oh man, I got to move this here a little bit. Oh, there it is. See how, now look at what's happening here. I should be able to adjust this guy. So I keep rotating this guy. I keep rotating until that ray is, you see how it's parallel. That's exactly what you want right there. That's why we're using the flat side on this so that you could pick this guy. So now, and I find what I found here is that I adjusted both the laser and I rotated the acrylic, half circle acrylic, until I got that to happen. So here's what we're doing here. So my image should then be like this now. So when I get this, what am I actually seeing here? So here we go. So what do you got to do? You got to create the normal. Use your protractor to create a normal here. So let's say that here's my interaction point right here. So what am I going to do here? What I'm going to do here is that I'm going to do this. I'm going to draw a line where this is parallel to the boundary, just like we did before. Here's my boundary line, right? Looks like I didn't draw it very well. Here, let's try this one more time. Oh, I did draw it right. The laser's not at the boundary. Okay, so here's my boundary. Then I need 3 points here, right? So here's my one for the refracted ray, and then we really don't need, for this, we really need 2 points just for the incident ray. So now what I'm going to do here, I'm going to assume that this is my normal. Here's my normal. And you could see here that this angle right here, which I'm going to draw in green here, this here is this is my refracted ray here. So now what I'm going to do here is essentially, what am I going to do? I essentially want to take, once I do those dots things, what I'm going to do here is that I've got to create those rays again. So I'm going to do this right here, and this is what I end up getting, right? After I remove that half circle on the laser, it looks like this. So now look at my ray. So now this is my incident ray. I'm going to do this long, right? Draw this long. So here I go. Here's my incident. We know that this is index 1 of acrylic. Out here, we know that this is index of air. So then check this out. This angle is my critical angle. My refracted angle here, theta 2, is at 90 degrees. So now I could go in and I can compute the index of refraction here. So that means I could then go in and I could now set this up here. So what you're going to do here is that what you're going to see here is that at that angle, you're going to see that there's a second angle. Okay? There's a second ray, and this is the reflected ray. Since this is a reflected ray, this angle should also be a critical angle. So to try to get better measurements, here's what I'm going to do. I'm going to call that CA, and I'm going to call that CB. So what I'm saying here is that do this here. You know the acrylic index of refraction, so then do 3 measurements. Go 1, 2, 3. And what I mean by this is that measure CA in degrees, measure CB in degrees, and then go in and get the average of these things. So the critical is going to be really CA plus CB divided by 2, and then go get the average. So now you have an average. Now, how do I get 3 measurements? What I would do here is that I would go in and I would pick up the half circle, move the paper, and then go in and adjust it again so that you can get a different measurement. So just repeat the measurement 3 times. So that means remove half circle and then repeat the process. Remember, science is about making multiple measurements so that you can create a confidence interval. Then as before, just like we did before, I could come over here and what do I want to do? Dude, it's the exact same thing as right here. There's no difference. I could come in here and it's always the same. Okay? So in this case, now what do I want you to do? Enter your average. In this case, it's going to be what? Theta critical into the Google Sheet. What do I want you to calculate? I want you to calculate theta critical of the class, but this time, let's call this C1 because it's the method 1, and then you have 2 sigma of C1. So you don't have the acrylic. What you have here is that you have a critical value. So then in this case, it should be theta critical 1, theta critical 1. But we're not going to talk about consistency this time. So there's actually, I've got to erase this. There's no consistency. So what this is really doing here is that we're having theta critical 1, 1, theta critical 1, 1. Okay, so now let's go to method 2. Method 2 is a pretty interesting situation. And so what we're going to do here, let me, where am I looking at? Here, give me a moment. I feel like I have a mistake someplace. I don't have a mistake. I thought maybe I had a mistake in something. I don't. Here we go. Now, here's what you want to do here. So what we're going to do here is that we're going to create a second distribution for method 2. And this, what you're going to do here in method 2 is that you're going to measure a, how do I call this? You're going to measure a circle on the half sheet or half circle. And what you do here is that you're going to take, what you find here is that here's your half circle. And your half circle has some paper. And that paper is rough here. So what you're finding here is that when you're looking at this half circle, this right here is rough paper, which then means that you get diffused reflections. And so what you're going to do here is that you're going to take your laser light and you're going to shine it straight down onto this paper, onto your half sheet. And what you're going to see here is that because there's a spread in the beam comes down, and because there's a slight spread in the beam, what you do here is that you get this diffuse scattering that goes all over the place. But it can't go all over the place because at one point, guess what happens? You reach the critical angle. And that means here that there's that over here, because you've reached the critical angle right here, what you'll find here is that you'll get a dark spot, okay? You're going to see a dark spot in your circle here. So you're going to see an intense, let me be careful here. So you're going to see an intense bright beam in the middle. So you'll see an intense, small, bright spot, and that's the laser, and that's because it's less than the critical angle. And then what you're going to see here, let me not make this so far. And then what you're going to find here is that in this spot right here, no light is refracted. So therefore, this implies that you see a dark circle. So then what you're going to find here is that eventually the beam will come back out, and then you're going to see a little ray right there. And so what you're finding here is that, remember this spot, I should be really careful. This red spot is really tiny. Okay, it's a really tiny spot. And so what you're going to find here is that this here then gives you half of the radius of this beam here. So this black beam from here to here, this gives you, this is a half circle. Half, how do I say this? It's 1/2 the radius of the circle. Whereas the radius is the full extent of this guy. So what I'm saying here is that I'm saying this here, is that the light scatters in all directions until the rays reach the critical angle and then stop reflecting the light into our eyes. So what we'll do here is that we want to use basic trig, triangle, and trig relationships to determine theta critical. Okay, so what you're going to do here is that, let me redraw this thing. So let's say that this is my, the edge of my half circle. And what you're going to see here is that this thing represents the thickness of half circle. And just because thickness starts with T, I'll call that T. So what you're seeing here is that this is what's happening here. Because that spot is so tiny, the center is so tiny, what you're seeing here is that the light you cannot see until, so from here to here, I'm saying here is that this here is the radius of circle. Okay, that's the radius of the circle. In other words, when you look at this guy right in here, this means that this whole thing here, this whole area, you cannot see any light due to total internal reflection. So I have a triangle now. So what I can do here is that I measure the radius of the circle. Okay, so so that means all along here, you're getting this black circle right here. This guy represents the critical angle. But if that's the radius of the circle, you could see that one of these edges is half the radius. So that means if I set up a triangle, my triangle looks like this here. This is my critical angle, and the distance from here to here is 1/2 the radius. So it's at this edge right here, you see this edge in the circle here. You see it in the circle. So now look what I got to do. I know that this is the height, the thickness T. So if I measure the radius of the circle, then what you're seeing here is that I can use the relationships of what? The opposite over the adjacent is going to give me tangent of circle. tangent of a critical angle. So then this means here, if I just use trig, we see that the opposite divided by the adjacent should be tangent of theta critical. So therefore, theta critical should be tan inverse of r over 2 divided by t here. So now, here is my value right there. So what do I want you to do? Set up a table and make the measurement. If you know your set up a table, so you know your thickness, let's say in centimeters, you know your radius in centimeters, and now make the calculation to get your angle. I mean, it would be preferable that you do this multiple times here. And then try to get an average for the critical. And so then what do I want you to do? I want you to do the exact same thing. What am I going to do? Check this out. I'm just going to copy this. We always do the same thing. This is science. Go in, do the following thing. So now I enter your value. This is method 2, so I'm going to call that 2. So instead of 1, this is 2, C2, right? So maybe this time what I'll do here, instead of red, let's make this green. So then I'm going to come in here, and here's my curve. And this is, instead of 1, this is 2. So now I have 2 distribution curves. So we have 2 distribution curves. And this implies here is that if I do what? If I take this curve, right? If I take this curve, then that means that if I look at this guy, right? So if this is the curve here, then I'm going to paste it twice right here. Now I'm going to go get the other one. So if I go get the other one, here's my red one. I'm going to copy that and I'm going to go down. So if I have these distribution curves that do not overlap, right? If they do not overlap, this implies is that the critical angles are not consistent with each other. A very important piece in calculations. On the other hand, if these guys overlap, right? If these confidence intervals overlap, and you could see here is that if I look at this guy, they're overlapping right here. So here, if they overlap, they are consistent with each other. And both measurements measure the same value. So that's those 2 pieces here, okay? And so another thing here is that note that there's a theoretical calculation because we know that N1 sine of theta critical should be N2 sine of theta, of 90 degrees. So the question is, does this guy fall within the confidence intervals. Right? That's ultimately what we're trying to figure out here. Okay, I think I'm going to stop now because I've already talked too long. Okay, but those are those labs right there. You'll see that the last piece is fairly light, and I think I'm not going to go over it. Okay, let me stop here.